Hello everyone, this video covers sections 6.3 and 6.4. Now the main idea of section actually of all of chapter 6, so the main idea of chapter 6 is the following. So we have a collection of random variables, okay, so these are random variables, and we're gonna define a new function that is gonna depend on the random variables. And pretty much we're interested in finding, so we need to find the probability distribution function of u. For that we have three methods. 6.3 is the first method, 6.4 will be the second one, and 6.5 is the third one. So the first method is called the method of distribution functions, and like the name suggests, we're going to use a distribution function. So the idea is going to be the following. So we want to find a distribution function of u, and we're going to use chapter 5 to do this. So we have done this before. Remember, this is the probability that capital U is less than or equals to lowercase u. Okay. So the hard part is that you need to find a region. So we need to find a region in the y1 all the way to yn space such that u is less than or equals to u. So this is the hard part. So once you do that, then you can find the probability that u is less than or equals to u by using the methods from chapter 5. And remember, once you find once you find the distribution function, which is this one, then you want to find the probability density function. All you have to do is take the derivative. Okay, so the derivative with respect to u of f of u, that will give you the probability density function you're trying to find. Okay, so that's how the method is going to work. So let's do an example and see how this actually works. All right, the example says the following. The amount of flour used per day by a bakery is a random variable y that has an exponential distribution with mean equals to 4 tons. Now the cost of the flour is proportional to this new variable. So notice that this is in one variable only. We're going to do two variables in a little bit. So this is what we have so far. We know that y is exponential with the mean is 4, which means that f of y is equals to 1 over 4 e to the minus y over 4, and y is positive. Now we also need the distribution function. Remember, the f of y is the same thing as the probability that y is less than or equals to y. So by definition, this is the integral from 0 to y of f of t dt, and if we integrate this is minus e to the minus t over 4 from 0 to y. So this will be minus e to the minus y over 4 plus 1, or just 1 minus this. So this is the distribution function for y. Right, so therefore, if we want to find the distribution function of u, this is by definition the probability that u is less than or equals to lowercase u. But remember, u is equals to 3y plus 1. So then this is the same thing as the probability that y is less than or equals to u minus 1 over 3, which is the same thing as the distribution function now of y evaluated at the point u minus 1 over 3. So if we plug it in here, we will end up with 1 minus e to the minus u minus 1 over 12. And hence what we really want, what was the probability distribution of u? Well, this is the derivative of the distribution function. So in this case, this will be 1 over 12 e to the minus u minus 1 over 12. And that's it. Where here u has to be more than or equals to 1. Now, notice that if I ask you to find the expected value of u, you can just use the results from before. The expected value of u is the same thing as the expected value of 3y plus 1. So this is 3, the expected value of y plus 1, which is 3 times 4 plus 1, and that's equals to 13. Now finally for this problem, notice that the distribution, probability distribution or density function of f of u is almost exponential. If this was minus 1, then this will be an exponential function where the mean will be 12 instead of 13. But this is not quite exponential because of the minus 1. All right, let's do one more example where we have only one variable. So here y has a beta distribution. So remember that means the density function is equals to gamma of alpha plus beta divided by gamma of alpha, gamma of beta, and then times y to the alpha minus 1, and then 1 minus y to the beta minus 1, and y is between 0 and 1. Let's say that we're interested in finding the density function of u, which we define as 1 minus y, where y has this density function. Okay? So remember, the first thing we need to figure out is what is the distribution function. And again, by definition, this is equals to the probability that capital U is less than or equals to lowercase u. Okay, so this means to find the probability that 1 minus y less than or equals to u, if you solve for y, this is the same thing as the probability that y is greater or equal to 1 minus u, which is the same thing as 1 minus the probability that y is less than or equals to 1 minus u. But this part is the distribution function of y. So this is 1 minus the distribution function of y evaluated at 1 minus u. Okay? So this is what we have so far for the distribution function of u in terms of the distribution function of y. Now what we really want is what is the density function of u. Remember, to find the density function, you have to take the derivative. So we take the derivative of the distribution function, and if we use the chain rule, this will be 0 minus the density function of y times minus 1. So this is just f of y evaluated at 1 minus u. So we use this formula and just plug it in there. We will end with this is equals to gamma of alpha plus beta divided by gamma of alpha, gamma of beta, and then this will be 1 minus u to the alpha minus 1, and then 1 minus u, it will be u to the beta minus 1, and this is true for u between 0 and 1. Okay, now let's try an example with two variables. So the total time from arrival to completion of service at a fast food outlet, y1, and the time spent waiting in line before arriving at the service window is y2, are given in exercise 5.5 by this joint density function. So here there's a typo. This one should be 0, then -1. Then we need to have the graph where we're integrating. So notice that this is y1. We have done the similar graph to this multiple times. This is y1 equals to y2. y1 less than y2 will be this part, and this keeps going to infinity. And here we are focused on finding the distribution of u, which will be y1 minus y2. So remember, we need f of u, lowercase u. So this is the probability that y1 minus y2 is less than or equals to u, which is the same thing as the probability that y1 is less than or equals to u plus y2. Also notice that here we need the line here, which will be y1 minus y2 equals to u. Hence the integral will be obviously double integral. Sorry, this will be e to the minus y1 the y1 the y2, where y1 will go from here to here, which will be y2 to u plus y2. So now we say you solve for y1 will be u plus y2, and y2 obviously is going to go from 0 to infinity, because this keeps going forever. And then if we integrate, this will be the integral from 0 to infinity of minus e to the minus y1 from y2 to u plus y2 dy2. And if we integrate again, which you should check this part, this is basic integration, it will be e to the minus u times e to the minus y2, e to the minus y2 from 0 to infinity. And once you plug in the limits, this will give you 1 minus e to the minus u. So then if you take the derivative of this, so this implies that the density function of u, it will be just e to the minus u, which this is exponential, where beta is equals to 1. And that's it. All right, let's try another example. So let's say that this is the density function for f1, this is the density function for y2, and here let's say that these are independent. So if they are independent, that's going to make life easier. And then define u to be y1 times y2, and obviously we want to find the density function of this. Now, since y1 and y2 are independent, so independent makes life easier, because that means that the joint density function of y1 and y2 is just the product of the two functions, which in this case, this will give you 18 y1 times y2 squared times 1 minus y1, and y1 and y2 are less than or equals to 1 and more than or equals to 0. Right, so therefore we need to find f of u. So again, this is the probability that y1, y2 is less than or equals to u, which is the same thing as the probability that y1 is less than or equals to u over y2. Okay, notice that the area of integration is the following. So this is y1, y2. And notice that since y1 and y2 are less than 1, that also implies that u has to be between 0, 0 and 1. So that's very, very important. And also notice that you have u over y2, that the graph is going to look like this, which is essentially like 1 over x. Okay, stuff like this. So that will be the graph of u over y2. Now it's going to be easier to integrate the following. The opposite of this is obviously this, because remember the probabilities have to add to 1. So this is the same thing as this, which is the same thing as 1 minus the double integral of 18 y1 y2 squared 1 minus y1 dy1 dy2. So y1 is gonna go from u over y2 to 1, and y2 is gonna go from u to 1. Now the integration here is pretty easy, but it takes a while, but it's technically self-explanatory. So this will be the same thing as the integral of from u to 1. If we integrate this will be 18. You can take the y2 squared out, and then this will be y1 squared over 2 minus yq 1 over 3. All of this from u over y2 to 1 dy2. Now again, this is just integration, which takes a little bit of time, so you should all check this. At the end you're going to end there with 9u squared minus auq plus 6uq ln u. And remember, this is true for u between 0 and 1. So therefore what we really care is the density function, which you have to do is just take the derivative. So this will be 18u minus 24u squared plus 6, and then this will be times 3u squared ln u plus uq times 1 over u. And then this will be 18u minus 24 u squared plus 18 u squared ln u plus 6 u squared, and then you can combine this more you want, but this is okay. Okay, so that's it for this method. So let's go to section 6.4 and look to the next method. All right, the method of transformations is based on the idea of section 6.3, but it's slightly different. So here we're going to have u to be a function of y. The difference here is that h has to be either increasing or decreasing function. So you need to check for this. So the idea is the following. We're still gonna do the distribution function, but now remember u is going to be a increasing function of y, and assuming that you can find the inverse function, that's why you need to have an increasing or decreasing function. This is the same thing as the probability that h inverse of h of y is less than or equals to h inverse of u. Okay, which is going to be the same thing as just the probability that y is less than or equals to the inverse function of h evaluated by u. Okay? Or, in other words, this means that the distribution function of u is related to the distribution function of y by an inverse function evaluation of u. Okay? And obviously from here, what we want, remember, was the density function. So then you just have to take the derivative. So this will be the derivative respect to u. But in this case, you have to be careful because of the you have to use the chain rule. So this will be the density function of y evaluated the inverse function times the derivative with respect to u of the inverse function of u, which is just technically the chain rule on calculus. Okay, let's try one example. In section 6.3, we did the following example. U was defined to be 3y plus 1, where y was an exponential function that have a mean of 4. Or in other words, remember that f of y was equals to 1/4 e to the minus y over 4 when y is equals to 0. Alright, so here we have h of y is equals to obviously 3y plus 1. Now, since this is a linear equation, it is very, very easy to find the inverse. So you remember from algebra, the inverse function of u is going to be technically just u minus 1 over 3. So you should check. Remember to find the inverse, and this is from pre-calculus. We have u equals to 3y plus 1. You change x for u, and then you solve for u. So u will be y minus 1 over 3. So this will be the inverse function, which is what we have right here. Right, so hence, remember what we want is what is the density function of u. So this will be f of y evaluated at the inverse function times the derivative with respect to u of h inverse of u. So this will be equals to the density function of y evaluated at u minus 1 over 3 times the derivative of this. So notice the derivative with respect to u of h inverse of u is just equals to 1/3. So therefore this will be 1/4 e to the minus u minus 1 over 3 times 4 times 1/3. So this will be 1 over 12 e to the minus u minus 1 over 12, which is exactly what we got in 6.3. let's try another example. So let y be a uniform function between 0, 0 and 1. So remember, this is a and b. So that means the f of y is 1 over 1 minus 0, which is just 1. And define u to be minus 2 ln of y. So therefore that means that h of y is equals to minus 2 ln of y. So to find the inverse, remember that this means the following. You have ln of y is equals to minus u over 2. So you solve for y. Y will be equals to e to the minus u over 2. So that means the h inverse of u will be e to the minus 1/2 u. And the derivative with respect to u of this will be minus 1/2 e to the minus 1/2 u. Therefore, from here, f of u will be equals to f of y evaluated at h inverse of u times the derivative with respect to u of h inverse of u. Exact same formula we did. And now notice that this is equals to 1, so this will just be 1 times this derivative. And this is true for u greater or equals to 0. So notice that this is just minus 1/2 e to the minus 1/2 u. And this is exponential with beta equals to 2. And that's it for section 6.4.